Welcome to EDU World Space.
So in this video, we're going to work through problem 54 from chapter 20, which says, using data from appendix 4, calculate delta H, delta S, and delta G for the reaction of N2 plus O2 forming 2NO, where all our reagents and products are gases. Why does NO form in an automobile engine, but then does not readily decompose back to N2 and O2 in the atmosphere? So before we pick apart that last question, let's go ahead and calculate delta H, delta S, and delta G by first visiting Appendix 4. So in Appendix 4, we have delta H and delta G in units of kilojoules per mole, and we have the entropy S in units of joules per Kelvin mole. And then your book lists these thermodynamic data for compounds both in the gaseous phase or in solution or in a liquid or solid phase. So you need to make sure you're looking at nitrogen, oxygen, and NO in the gas phase. But anyway, this would be the data that you would get from Appendix 4. So let's plug this into our calculation for the enthalpy, where we just take the products minus the reactants and we multiply each reagent by the stoichiometric coefficient. So we have 2 times NO, which is 90, minus 0 and 0 for N2 and O2. And that gives us 180 kilojoules per mole for our change in enthalpy for this reaction. What about Gibbs free energy? Well, we do the same thing. We take products minus reactants, and our reaction is still N2 plus O2 yields 2NO. So we have 2 times NO, which is 87, minus N2, which is 0, minus O2, which is 0. So 2 times 87 gives us 174 kilojoules per mole for our Gibbs free energy. And then for entropy, we do the same thing again. We take products minus reactants and we multiply everything by its stoichiometric coefficient. So we have 2 times NO, which is 211, minus N2, which is 205, minus O2, which is 195. So that works out to 25 joules per Kelvin mole. So what does delta G tell us? We know that a reaction is spontaneous if it releases free energy. Remember, free energy is energy that's available to do work. So we need to release free energy in order for this reaction to be spontaneous, which means that we need delta G to be negative. That would correspond to releasing energy. So is delta G negative in this case? Well, delta G is 174 kilojoules per mole. That's greater than 0. That's positive. So this reaction, where N2 and O2 combine to form NO, is non-spontaneous at standard temperature and pressure. So how does this reaction occur in an engine? How is that happening if we have a non-spontaneous reaction? Well, we've said that this is non-spontaneous at standard temperature and pressure. The delta G tabulated values in Appendix 4 were for standard temperature and pressure. But what about other temperatures? Because our engine isn't at room temperature. So we can also calculate delta G at temperatures other than our standard 298 Kelvin using this equation, which is delta G is equal to delta H minus T times delta S. And we can assume that delta H and delta S aren't going to change as we change temperature. So the delta H that we calculated was a positive number, and the delta S that we calculated was a positive number. So in order for this equation to evaluate to a negative number, in order for delta G naught to be less than 0, that second term must be larger than the first term, since we're subtracting the second term from the first term. So that's going to be negative if T times delta S is greater than delta H. And when is T times delta S greater than delta H? T times delta S is greater than delta H if the temperature is large. So T needs to be large in order for delta G to be negative, and that makes sense. We need to be at a high temperature in an engine, so this reaction would occur spontaneously in your car, but it would not occur spontaneously at room temperature. But remember, we're asked, why does NO form in an automobile engine? We've answered that part of the question, but then does not readily decompose back into N2 and O2 in the atmosphere. So why wouldn't it decompose back into N2 and O2 in the atmosphere? So we just worked out that at standard temperature and pressure, which would apply to our atmosphere, N2 plus O2 forming 2NO is a non-spontaneous reaction with delta G greater than 0. And remember, we calculate delta G as products minus reactants. So if we flip the direction of our reaction, we just flip the sign on delta G. So for the reverse reaction, the decomposing of NO to N2 and O2, that reaction should be spontaneous. So why wouldn't these decompose in the atmosphere? Well, remember that the spontaneity of a reaction is totally unrelated to the rate of the reaction. So just because this decomposition is a spontaneous reaction with a delta G that's less than 0 and negative delta G, the rate of the reaction could be so slow that it's not observed. So the reason we would not see this in the atmosphere would be because of the rate of the reaction, despite the fact that it occurs spontaneously.